We'll be moving on to our next lecture. I can see that Dr. Vaishak has joined us. Once again, he'll be speaking on logic meets learning from Aristotle to neural networks. Please, Dr. Vaishak, you can speak to us. Thank you.
Yeah, can you hear me?
Yes, we can.
Yeah, I'm not, because I'm sharing, it seems I can't put on my video. But can you see me? You can't, right?
We can see what you are sharing, but we can't see you.
Okay. So shall I proceed this way or shall I figure out? Oh, yeah, okay. What about now?
This is
Now
okay.
you can see me, right? All right. Let me start this way then. If you can't hear me, please put it on the chat. So hi, everybody. Thanks again to be presenting here. It's super interesting. I had to step out briefly for personal reasons, but the topic of this colloquium is really interesting because what I was going to talk about, and the title is slightly changed from my initial title, is an area which I think is relevant to what's being discussed here, is the course of where logic and learning come together. And I'm speaking about a very specific application of this integration, which is called as neuro-symbolic AI. I'll talk a bit about other ways of doing this too. And again, if you have any questions, please put them on the chat. Or if you stop hearing me abruptly, please let me know. So I'm at the University of Edinburgh, and what I will talk about today is this idea, which I think the last talk was just going on about. There seems to be some sort of tension, but this is not really a point of tension. I think this is a point of interesting collaborations. But there's a point of tension uh, between a deduction and induction. So deduction, we typically say, we have some sort of knowledge base and we're interested in a query. We might apply some sort of semantics or some sort of proof theory, and then we'll ultimately deduce some property phi from delta. Usually, we are interested in phis that are not explicitly mentioned in delta, right? So for instance, given the rules of chess, you might be interested in knowing, is there a strategy that guarantees that I win the game? What's also interesting with deduction is when you go into the first order setting, where you can have quantifiers. So for instance, this one says that everybody who is a smoker happens to have a friend. So maybe I'm interested in saying things like smoking is a social contract, right? So when you have friends who smoke, maybe you feel obliged to smoke. So that's deduction. Amara, you can still hear me, right? Just let me know if you don't, okay?
We can hear you.
Good. So on the other hand, you have learning. And again, learning is many different things. If you go back to Aristotle, he had a very specific notion of learning. Mainly what he was interested in was this idea that you want to generalize from instances. Okay, so if I see that all swans are white, then I want to say something like, well, I know for a fact that all swans are white, and then maybe I'll see a black swan, and then I'll revise my beliefs. Okay, so but generally, you could think of this idea that you have some sort of generalization from a specific set of instances, specifically in the context of AI, which is what this colloquium is about. We often say these instances are drawn from some distribution, okay? So if you want to apply this to the real world, you might say there's some sort of distribution that determines that the sun, rises every day. And then you take a generalization, you say, well, the sun rises every day, right? But again, we do know from physics that the sun will probably die out in a few billion years. So this distribution is not known to us. In some cases, we can estimate it, but we don't know this in general, okay? Or you might see images of cats, and then you say, well, this is what a cat looks like. So have some sort of, description, or stochastic description for a cat, okay? So One of the interesting questions, of course, in philosophy, AI, cognition, logic is how do you bring these two things together? And I don't discuss this here in the interest of time, but there's an interesting history going back to Aristotle. And I'm afraid in the context of specifically the last discussion, what I'm aware of is mostly from the Western tradition, although I expect there will be many interesting insights from the Eastern tradition and the African tradition too, to contribute to this. But mainly I've been reporting on the Western tradition. So people like Aristotle, David Hume, Rudolf Carnap, these are logicians, and they were interested in, well, how do we make inferences about the world, right? We observe things, we make judgments. How does this happen? So perhaps the most refined treatment of this is the integration of logic, probability theory. So probability theory captures noise or uncertainty, and then you have learning, which is basically drawing some inferences from these distributions. Okay. If you're interested, there's a book chapter from 2 years ago that I wrote that just summarizes what's happening in the field. But I'll try to give you a picture here. Okay. So there's many modern flavors, as I said. What I'll be talking about in this presentation is one instance of this called Neuro-symbolic AI. There's other areas. So in the 90s, one very popular area was something called statistical relational learning. So basically the idea here was, well, if you have first order structures, how can you learn them? There was also something called inductive logic programming. Maybe many people in this audience know about this. And the idea there is, how can you learn things like logic programs? So basically these are Horn clauses. How do you learn Horn clauses from data? And if you go back even further, in the 1960s, people were building robots. And many of these robots actually were kind of had a stochastic element, obviously, because it had to deal with sensor noise. But there was also quite a bit of decision making, which was kind of logical. I would not say it's necessarily deduction, but it did have some sort of symbolic processing, including treatments of language. Okay, so quite a long history, and there are many dimensions of this thing. So, for instance, you could say, why do logicians care about machine learning? Well, they may want to care because logicians can be expected to provide the knowledge all by themselves all the time. So maybe from data, you want to do some learning of axioms or logical sentences or whatever. So one factor is, can machine learning contribute to logic, right? So that's learning of logical artifacts. You could also reverse the question. You can say, what can we do for machine learning in AI using logic? Okay, so, that's something I'll talk about here. Okay, so that's mainly what I'll focus on, although there has been quite a bit of work that we've done also on the first point. The third point I think is more interesting. Maybe this was again related to the last talk, because the question is, are there places where you can compete between logic and learning? So what does that mean? Are there things that I can do better with logic? And are there things I can do better with learning, right? So if you think about the chess problem, I think this was a question asked. I mean, if you have a chess problem, is it better that I solve it using deduction, or is it better that I train a neural network and solve it? And what is the cost for training this network, right? So you might want to take computation as one way of thinking about what does it mean to say better, right? So how much effort am I spending to learn to train the network? And maybe it's more expensive to train it than to solve it using deduction. So things like this, okay? So these are the three main dimensions as I see between logic and learning. So why neuro-symbolic AI? Okay, so this is what I said. It's a very specific instance of logic and learning. And maybe the reason is obvious at this point. I mean, deep learning is everywhere. And what's interesting about deep learning is that it has a very large hypothesis space. But what also makes it less interesting or uninteresting or even bad is exactly that, right? The feature is also a bug. Okay, so because it has such a large training space, it is incredibly expensive to train. The last I remember is asking, questions to ChatGPT is about 1,000 times more expensive than asking questions to Google, the normal Google search, like the old Google search. So it's very expensive to train it, okay? And of course, they struggle with structure, right? In logic, we talk about structure using connectives or quantifiers. They struggle with structure because of the large hypothesis space possibility. You need a lot of data to train it, okay? It's difficult to integrate knowledge, right? So sometimes you have experts, like medical experts, who have ideas about the domain, and it's difficult to put it into the network. Um, there's also explainability. These networks are basically black boxes. And of course, they're nothing like the brain, right? So the brain neurons are bidirectional. Neural networks are unidirectional, so that you train them in the forward direction, and then you then pass a gradient back to the network. But even then, they are completely opaque. Just like we don't understand how the brain works, even at a simpler level, a neural network is also inexplicable. Okay, it's not hard to understand, and of course, because of this, you don't have guarantees, right? So there are many nice anecdotal examples. So you train a network to pick up images of bottles, and it might come back and say a bottle is anything which has a gray background, because all your training images had a gray background, right? So you don't really know if it's actually learned what you wanted to learn. So these are issues about neural networks. And the question then is, can logic fix some of them? Okay, can logic help in fixing some of them? This is a kind of impressionistic diagram of what this looks like. So on the left-hand side, you have logic, right, where typically you deal with things like deduction and abduction. You also have induction in there. So that's why I mentioned inductive logic programming. And as soon as you take the induction part of this circle, the overlapping with machine learning, you start getting areas like relational learning and so on. Okay. And again, machine learning typically is based on a probabilistic semantics. And specifically in machine learning, if you look at deep learning, then you get this area of neuro-symbolic AI. Okay. Amara, can I check how much time I have? Am I halfway through or?
You still have time. 12 more
Like
minutes.
halfway through, like another 15 minutes or? Okay.
12.
Okay. Yeah. All right. So that's essentially the area. I hope that gives you a sense of the motivation and the landscape, okay, for logic and learning, and specifically neurosymbolic AI. So let's look at a few exciting areas, and I'll talk about a couple of them with some work we've done. Okay. So as I said, one of the big problems with deep learning is, how do you put knowledge into the network? Okay. So if I'm making predictions about cancer patients, how can I include some knowledge about, the symptoms of cancer, as well as what other related symptoms might appear, and how this might connect to habits like smoking, or even genetic factors, or like the predisposition for cancerous tissues and so on. So how do I include all of this knowledge? So this then becomes this area of knowledge graphs, which is an exciting area. I'll talk about this second area a little bit more. It's this idea of constraint prediction. Okay, so constraint prediction is basically when you want the machine learning system to uh, kind of make sure that it obeys the laws of physics and geometry, or any other kind of constraints, really. I mean, we've also looked at constraints like ethical constraints, fairness and bias. All of these issues can be seen as constraints, and how do you make sure the machine learning system obeys these constraints? And then if you want to talk about how is the system correct, then there is properties that people have come up with, like robustness and safety, and how do you check, the properties of these systems, okay? So I'll do in this talk three things, just as a kind of teaser of what you can do with logic and learning, specifically in the neuro-symbolic context. I'll talk about loss functions, program induction, and what I call a large language model as a service. Okay, they're quite different in the types of logics they consider. The first one is propositional, the second one is first order, and the third one is modal logic, epistemic logic specifically. Okay, so that I think is the other nice thing about these three topics, that they hit on different types of logics. So what's the first one about? So as I said, one of the big problems with neural networks is that we apply them in the real world, and we have lots of real world constraints, but you don't really know how to make sure that the network understands these constraints. Okay, as a very simple example, you could be using a neural network for some kind of road network or a railway network or an airplane pathway network or just a road network with cars, and you want to make sure that the network always predicts points that never suggest an impossible path, right? So if I'm flying from, say, London to New York, I don't want a path that basically says, well, go under the water and stay there until you get to New York, right? So you don't want those kinds of things. And in a very abstract way, it's a bit like saying, look, here's a rectangle, and I want to make sure the predictions only fall into these blue rectangles. Okay, you have a bigger rectangle, and I only want to fall into the blue rectangles. And how do you do this? And surprisingly, even at this level, a neural network is very bad. Okay, so you can, if you provide the training data for this network, what can happen is that it can produce a lot of invalid data points. But if you ask any sort of mathematician or a logician, he can very easily say, look, all you have to do is you can describe these rectangles using constraints like this, right? So you define points or bounding boxes on the X and Y axis, and that gives you the rectangle. So the question is, why can't we get the network to do this, right? And it turns out it's not easy to do. So the kind of approach that we've been doing, and not just us, there are a few other labs that are also investigating this, is why don't we find a way to force the network to treat these constraints as another kind of label, okay? So basically what you're saying is, here's my neural network, and I don't really care what the neural network looks like. And in a neural network, you provide the input, and then you give labels to it, right? So for instance, I might give it images, and then I say, these are cats, these are dogs, those are people, and that's a sky, and that's a sun. Okay, so I give all of these data points to the network, and I train it, and the network looks at these images and gives a prediction, okay? And every time it makes a wrong prediction, I punish it, okay? So how do I punish it? I give a loss function, which says that every time you get the prediction wrong, this is a negative reward, and you pass it back to the network, okay? So this is how neural networks are typically trained. And what we'll do now is, along with this loss function that talks about how badly it predicts, I will also add another loss function that talks about how well it satisfies this constraint, okay? So that's a new loss function that I define purely using logic, okay? I don't go into the details in this talk for reasons of time, how exactly we do this, but that's the essential idea here. So you take some sort of propositional formula, and you play with the loss function to capture not just the alignment with the labels, but also alignment with the constraints themselves, okay? And when you do this, you basically get a network that satisfies the constraints, which is great, right? Which is what you wanted. And you can define all sorts of complicated constraints. Here's an example of how badly the network does if you don't give the constraints. As you can see in the bottom, it produces a lot of invalid points, even though your training data is good. And again, this goes back to the issue I said. Because the neural network's hypothesis space is so big, it just doesn't get enough training data to learn correctly. And as soon as you put these constraints, you can get the network to do the right thing. I just wanted to include this example, but I don't have to go into too much detail. One of the things you can do is you can get the network to learn digits. Okay, so for instance, you can, instead of giving it labels on the images, you can instead give it labels on arithmetic operations like summation and product and division. And the network will figure out, so if you give it as a constraint, the network will reverse engineer what each of the digits mean. Um, for time reasons, I'm just skipping that, but if you're interested, just reach out to me and I can share the details with you. Okay. Another piece of work, as I said, the first piece of work was in propositional logic. The second piece of work is, can we learn logical formulas and logical theories? What we do here is we use neural networks in the context of inductive logic programming. And roughly the idea here is the neural network is helping you deal with noise and nonlinearity. Okay, so just as an example, if you consider Einstein's a famous equation of relativity, that E is equal to mc squared, the energy is mass times the speed of light squared. The question to you is, can we learn these rules if you're given the data? So given purely observational data, can you learn the rules? And this is like the holy grail for logicians, right? Because looking at purely the generated data, the logician would like to learn the rule that works, okay? Again, I'll skip over the details, but roughly what you're doing in inductive logic programming is giving some examples. You're learning a hypothesis that entails all the examples, and you're ensuring that if there are any negative examples or negative instances, it's not entailed by the hypothesis, okay? So that's the idea of hypothesis learning in inductive logic programming, but of course we do this in a neural setting. And specifically, when it comes to this rule of E is equal to mc squared, we produce rules like this. Okay, so we basically, it looks a little complicated, but that's just because of the way inductive logic programming works. And it's basically saying, the product of the mass and the speed of light square is less than 0.3, and the speed of light is less than 0.5, and the mass is less than 6, then you can expect the energy to be in this range. And if you factor these results over a bunch of rules, you basically can recover E is equal to mc squared. Okay, so it's less direct, unfortunately, just because of the nature of the framework, but you can still learn theories about the physical world. And again, because you have logical rules, you can extrapolate from them and learn generalized quantified expressions. Okay, so that's quite nice. In a dynamic context, this is a problem called as a cart pole problem, where what you're trying to do is you're trying to balance a stick on your finger. Okay, and if you've ever balanced a stick on your finger, you know that if the stick starts falling to the left, you move your finger a bit to the left. If it starts moving to the right, you move it a bit to the right, and you can balance your finger. And we can get again the framework to produce rules like this, which says that if the position falls between certain values, then move left, otherwise you move it right. Okay, and you can imagine giving this kind of program. This is a first order program to the robot, and it follows these rules. Okay. The last piece of work I want to quickly touch upon is as I said, I talked about propositional and first order logic. I'll give you an example on mode logic, and this is some new work we've been very interested in. As you might be aware, modal logic is a very interesting area of research in many communities, not just in the Western AI tradition, Western logic tradition, because again, epistemics becomes an important part of how knowledge is learned, right? And one variant of epistemic logic is this idea of multi-agent logic. Okay, so essentially, you have a bunch of agents with different beliefs, and you're trying to figure out what everybody knows. As a simple example, you might be playing a game of cards, and I might pick up a card and see it, and I might show it to my neighbor, but I might not show it to you. And so then you start thinking, oh, wait, he knows his own card, and his neighbor knows his card, but I don't know the card, and they could play with each other or communicate with each other and strategize and beat me, right? So card games have competition. and all based on epistemic factors. Okay, so what we do in this work is we take so-called card game questions, which involve a bunch of agents, and use the large language model to translate it to what is called as a public announcement logic. Okay, public announcement logic is a multi-agent epistemic logic with announcements. So basically, I announce to this colloquium, for instance, that I'm currently based in Scotland, and this way everybody in this colloquium attending the Zoom meeting knows that I'm in Scotland, right? Or I might announce the laws of traffic in the UK, and you might compare it to your own rules. So that's what announcement logic does, and we can translate this to announcement logic. And again, interestingly and not surprisingly, and again, referring back to the previous talk, the LLM doesn't do deduction properly, okay? It makes a lot of mistakes, it guesses things. But what we can show is that you can pass it to a model checker and get correct answers. So the large language model is kind of a middleman, right? It's doing the translation from natural language to logic, but then once you have the logical expression, you use a model checker to compute the answers. So this is a nice way of getting correct answers, okay? I'll skip over this. I have some thoughts on how neurosymbolic AI could play a role with ethics. I have a paper that I wrote last year on the role that beliefs and actions play for ethical modeling, because if you look at mainstream work on ethics in AI, it's largely very propositional. So I argue that you need mental attitudes to actually come up with good definitions. And we have explored some work on that side, okay? But I'll skip over that. I'll share the slides with you if you're interested, but roughly the argument is that you need these epistemic logics combined with ethical constraints along with learning, okay? So to wrap up, as I said, neuro-symbolic AI is a very powerful and interesting paradigm, lots of open questions in terms of semantics. And ultimately, it is also beneficial to the logician, right? Because logicians have often been writing rules for so long, but maybe we now can use machine learning to learn some of these rules and check when they're correct. But the deduction machinery, we can compute the way we have done before using proof systems exactly. Okay, so there's an interesting role for machine learning to play. There's quite a bit to be said about ethical AI and what that means. You know, what does it mean for agents to be ethical, and what does it mean for the agents to perform correctly, and issues of alignment. But I think neurosymbolic AI does have something to say there as well, because it's able to combine symbolic and normative rules with machine learning data. With that, I thank you very much for your attention. Happy to take questions.
Thank you very much, Dr. Vaishak, for this wonderful lecture. Please, if you have a question for him, kindly raise your hand up, even a comment. I will call you to unmute yourself and ask your question. Okay, while we are still waiting for the audience to ask, okay, we have someone here. Please, Professor Ramesh, unmute yourself and ask your question or make your comment. Thank you.
Very interesting paper. Thank you very much. Actually, I'm very curious to know more. So I'd like your paper or your slides, if possible. Uh, yeah, I am obviously new to neurosymbolic reasoning and neurosymbolic models, so I just need to get more details on that before I can make any comment. But I enjoyed your presentation. Thank you.
Yeah, thanks a lot. Thanks a lot, Ramesh. I'm happy to. I've shared the slides already with Amara. I mean, maybe she can share everybody's slides together, right, Amara? Once the colloquium is over, and we can just see. But yeah, I'm happy to chat further, Ramesh, at any point.
Okay,
Thank you.
I will do that. Okay, in the absence of no further question or comments, we'll be moving to the next speaker because of time. I'm going to send my own question to you after this event.